We're going to start off with a fairly simple system, though, a pendulum. Pendulum that's going to oscillate back and forth. So I got a mass, and we're going to consider this to be a rod, so a stiff rod rather than a piece of string. And that's going to allow us to have this thing sort of fly over the rotating center of the plane here. If we look at the differential equation, what you get is that torque kind of equation where you've got the angular acceleration, and it's like ma, but because you've got lengths involved, it ends up having an L squared, so the length of the rod, that'll be that distance there, is going to play a role. And once you get past there, it turns, the other two forces are pretty straightforward. You've got yourself gravity, and you've got yourself some resistance, some drag, which is the friction force. I'm not a huge expert on rotational kinematics, so we're going to start with this thing as a given for us. The only thing we're going to do to make it look more like a differential equation that we've seen already in the class is divide by m and l. So there's an m and l squared here. We're going to divide by ml squared, and that gives us this new form here. What we want to do is move from this, which is our rule, and we want to get a simulation running. Right? We fully believe that the acceleration of this pendulum as it swings back and forth is dictated by the torques from gravity and the torques from friction. That's just how things work in a Newtonian world. But that doesn't let us predict, how long are the swings going to be? Will the thing go over the top if I started off with a strong enough push? All those result kind of questions, we need to simulate the motion to be able to answer those questions. So that's going to be our goal. Now, we're going to have to do an intermediate mathematical step before we do that, though. This is a second order dE, because it has two derivatives running around inside of it. If it has two derivatives running around inside of it, we have to do something funky with this. We're going to want to convert it to a pair of first-order differential equations. A little reminder here. We're going to create two new variables. We're going to let y1 be equal to theta. So this is the one that we have in our system. This is our new one right now. Okay? And we're not going to stop there. We're going to invent two new variables because we want two differential equations. We're going to make y2 be a new variable as well. And now that we've gotten this far, what should we make the second variable equal to? Oh, you're making your 225 instructor proud. All right. It's easy. Fortunately, this is the easiest part of the whole process. We're going to make two new variables, one which is theta and one which is theta prime. Why will we do this? Because it's going to work and give us what we need for the next stage. So, once we've invented those two new variables, what do? You find the derivative of each new variable. Okay. So y1 prime, we've defined our two new variables. This is going to seem circular, but it'll have an impact when we get to the end. y1 prime, which is its derivative, is going to be equal to the derivative of theta, because theta is y1. They're the same thing. Let's actually write it that way. So the derivative with respect to time of y1 is equal to the derivative with respect to time of theta, because they're the same thing, just different labels. That's going to be theta prime. But if I want to write everything in my new variables, what would that equal altogether? y2. Yeah, that's handy. So one of these derivatives is super easy. The other derivative is a little more involved, but it has exactly the same procedure. I want to find the derivative of y2. Well, that's the derivative of theta prime, and that's theta double prime. That's not obvious until we remember, hey, back up here, we had an equation that was theta double prime equals. So this is where we bring in the actual mechanics. So far, we haven't done anything with our actual pendulum configuration. Now we've got theta double prime, but theta double prime is equal to all this stuff here. And if you'll note, we have a theta in there, that's y1. We have a theta prime in there, that's y2. So we can write all of this, negative g over L, sine of not theta this time, but y1, and times some friction coefficient times theta times the velocity, which is just y2. That is a system of two differential equations. Notice 1, 2. They only involve the new variables y1 and y2, and it clearly represents my differential equation I started with, because there's my differential equation I started with, just with new variables. New variable names, really. That's all we did. So that is how we can transform, that's a lot of red and blue on that screen. That's how we can transform the second derivative equation with one variable into two first order, only one derivatives, equations with two variables. And that process will always work. Whatever original variables you have, make one of those your y1, and then as many derivatives as you need to fill in the rest, make those your y2, y3s, and then ask what's the derivative of each of those equal to, and express it in the new variables. Let's take a look then, and note something about MATLAB. MATLAB solvers like ODE 45 only handle first order systems of DEs. This is not a limitation, though, because we can always reduce higher order DEs to first order systems with exactly the same process. Y2 equals, sorry, I should say variable here. Variable. And so on. We can always do this process. It'll always work. It'll always turn a bunch of derivatives into one single derivative of each of the variables we created. So that's why, if you look in MATLAB, there is no solver for second order systems, because we don't need one. It becomes our job as users to convert what we have into the format that MATLAB can handle, and that means they only have to maintain and give instructions on single functions like ODE 45. So that's why you're going to have to do some work up front on these things to make your equations match what MATLAB's expecting.